this is a set of lectures on cosmology, and before starting, let me just give you a brief overview of what we are going to discuss during these lectures. This is tentative, it may change in the course, but roughly what I was thinking about is this. Today we are going to discuss homogeneous universe, so entire course on homogeneous universe is in one lecture. And then I will concentrate on cosmological perturbations, first in the bottom-up approach. And the reason is, of course, clear. The cosmological perturbations will tell us and are telling us a lot about the very first stages of the cosmological evolution. And therefore, it's worth discussing them in detail. So I will discuss cosmological perturbations in some detail, starting from elementary things like helicity composition. Then we'll discuss tensor modes, how they behave, vector modes briefly. And then we come to scalar modes, which is most complicated and, on the other hand, most relevant for the time being part. So we'll discuss various properties of the scalar modes, how they behave, what equations do they obey, etc. If I have time, we'll discuss what happens to them after recombination. And then we'll go to CMB, a cosmic microwave background, first temperature anisotropy, and then polarization, hopefully, which might become a hot topic, which was a hot topic and will be a hot topic, hopefully. Then we'll discuss, that's going to be independent of the, almost independent of the origin of these perturbations. But the main issue is, of course, the origin of these perturbations, and therefore we'll discuss in some detail inflation, which is the best and most popular mechanism of generating the cosmological perturbations. But then in the end, in the last lecture, we'll discuss alternatives to inflation, which is still an option, given that BICEP 2 is not confirmed yet. So that's the outline. And let me put this transparency back. So this is our first lecture. This is basically introductory part. Unlike other lectures, it will deal with homogeneous universe exclusively. So before starting, let me just say that as in many other cases, in many other lecture courses, we are going to use the natural system of units where h bar and speed of light and Boltzmann constant are equal to 1. And I give here a reference to a calculator of dimension full quantities, so that if you want to do calculations in weird units, like megaparsec, gigahertz, etc., still you can use this simple tool to convert into whatever unit you would like your final result. Okay, so let's begin. Let me begin with elementary things. I'm assuming that you know to a certain extent general relativity. I was advised that the GR is in your hands, at least in principle, but I was advised that cosmology is less known to you. So I'll begin with the beginning. So we are talking about homogeneous and isotropic universe, and the basic object is metric. In general, this is g mu nu dx nu. That's a general metric in GR, general line interval in GR. And then in homogeneous and isotropic case, you can choose your time variable in such a way that it's in here simply, and then the scale factor is a factor of time times the spatial metric for sometime I will stick to this metric. So that's one possibility. Then gamma ij is the one of three possible metrics, homogeneous and isotropic metrics of space. This is either metric of 3 hyperboloid, and the one assigns a parameter kappa equal to -1 to this case, or it is a metric of flat space, three-dimensional Euclidean space, and then this parameter is 0, and finally this could be a 3-sphere, and the parameter kappa is equal to +1. Okay? So that's the definition. There are only 3 homogeneous and isotropic three-dimensional spaces, which are sphere, obviously it's a homogeneous and isotropic, Euclidean space, three-dimensional Euclidean space is also homogeneous and isotropic, and also 3 hyperboloid. So in principle, one can think of open model, cosmological model, flat cosmological model, and closed cosmological model. The sphere is obviously closed, compact, manifold. Experimental fact is that actually this is realized in nature. But for the time being, I will consider a more general situation. So this is the metric of unit radius. So A can be viewed as, in this case, in these two cases, when metric is not flat, A is the radius of curvature. Of either hyperboloid or sphere, whereas in the Euclidean case, A itself doesn't have direct physical significance. By rescaling the coordinates, you can set it equal to 1 at a given moment of time. For example, today, it's often that it's completely conventional to set the scale factor equal to 1 today. I will not do that. But we should remember that A itself should not enter the finite physical answers. What is relevant is the ratio of the scale factors at different times. That tells you how much the universe has stretched, the space has stretched as time went from t prime to t, as the universe expands. Now, another notation is that we will use subscript 0 to denote the present values of all quantities. So T naught is present time, A naught, which is A of T naught, is the present value of the Hubble, of the scale factor, etc. That's again a convenient notation, and usually again this A naught is set equal to 1 by the choice of coordinates. Right. Now one should understand that xi's are comoving coordinates, meaning that if you put a point, galaxy, at a given value of x, then it will sit there. You can check, and that's a nice exercise, simple and nice exercise, that the xi equal to constant, this word line obeys the geodesic equation. Okay? So that if you put a galaxy in there and it doesn't interact with anything, it will stay there at a given coordinate x. Okay? However, the physical distances are, of course, not the coordinate distances. The physical distances are related to coordinate distances by this obvious relation, right? That the scale factor enters here. So the distances between the galaxies increase. That's the expansion of the universe. The space stretches out. Likewise, if you have a photon which is emitted at time t, this is time of emission, at wavelength lambda, then by today its wavelength will be different. The present wavelength will be equal to A0 over A of t times lambda, the emission, the wavelength at emission. Okay, that's tells you how much the universe has stretched from time t to today. And this ratio here is called 1 plus z, where z is redshift. That's experimentally measurable quantity, very well measurable quantity, because the wavelength or frequency at emission is determined by atomic processes, you know it, whereas the wavelength at that you receive is directly measurable. So that redshift is very well measured, and therefore it's convenient to use this parameter. Finally, as you all know, the expansion of the universe is characterized by the Hubble parameter, h equal to a dot over a. Okay? It depends on time, and its present value is a matter of little bit of controversy, but according to Planck, it's 67 plus or minus 1, roughly, in units kilometer per second per megaparsec. This rather weird unit, which has to do with the Hubble law, you can immediately find from this relation here that at small z, you have a Hubble law, which tells you that the redshift is equal to h naught times the distance to the object. This is a physical distance to the object. This is true at small z. It's straightforward to, use the definition of z here to figure out this Hubble law. So if you interpret this as Doppler shift, then z is the velocity, r is the distance, so h naught is velocity over distance. That's why it's conventional to use this weird unit here. But of course, h naught is inverse of time, as is clear from here. So h naught minus 1 is the typical time scale in the present universe, and this is equal to 14 billion years, which is accidentally almost equal to the lifetime of our universe. Accidentally. It's not that the inverse Hubble parameter should always be equal to the lifetime. It's proportional to lifetime, but not necessarily equal to it. Okay? Or if you convert it to the length scale, then this will be 14 billion light years, and this is 4,300 megaparsec. By the way, megaparsec is 3 light years. This is 3 times 10 to 24 centimeters. Okay, so this value sets the scale, the time scale and length scale in the present universe. Okay? By the way, if you have any questions or you don't understand something, just shout, okay? Not even raise the hand, but shout. I will not necessarily see the hand Okay? Any questions so far? Yeah, it's all trivial. Right, okay. So this is kinematics in a nutshell of expanding universe. So what is the dynamics? The dynamics is governed by general relativity, of course. Unless we deviate from general relativity, which is not impossible, but let's stick to general relativity, then the dynamics is governed by Einstein's equations, right? The expansion of the universe is governed by Einstein's equations. Specified to homogeneous and isotropic universe, I'm not going to derive equations for you in this set of lectures. This will be too long, too boring, and I'm pretty sure you're smart enough to derive them yourself, okay? Yourselves. So you have this metric here. You calculate the Ricci tensor, curvature scalar, and you write your Einstein's equations, which are, let me remind you, these equations here, 8 pi g times t mu. I have to say a word about the energy momentum tensor, t mu, the right-hand side. Sorry? Sorry. Right. Yes. Thanks. Riemann curvature, Riemann scalar. Okay, so I have to say a few words about the homogeneous and isotropic energy momentum tensor. If you have homogeneous and isotropic universe, then the energy momentum tensor must be also homogeneous and isotropic, which means that it can only have the following components. Not component, which is rho, which is energy density. In this metric, it's precisely the energy density. And the only other components are the spatial components, ij, which must be proportional to gamma ij, to the metric you have here. Now, in local Lorentz frame, this would be, in the case of perfect fluid, this would be pressure. This is true in locally Lorentz frame. However, we are not in locally Lorentz frame. We have a scale here equal to a. So the correct expression here is a squared times p times gamma ij. So that, and this p is effective pressure. For perfect fluid, it's just pressure. That's the only homogeneous and isotropic tensor you can have in your universe. Now you can check, of course, that Ricci tensor also has the same structure. It has non-vanishing not components, and its spatial components are also proportional to gamma ij. Okay, so these equations are consistent, and there are only two equations that survive. One is the Friedmann equation, which I will use often, and it has the form a dot over a squared, which, remember, is h squared by definition, and it is equal to 8 pi over 3g rho minus kappa over a squared, where kappa is precisely this kappa here. Okay? So, as I told you, the scale factor has the meaning of spatial curvature, and this term comes from spatial curvature inherent in the Ricci tensor. Okay? This is called Friedmann equation. This is one of the equations we will be repeatedly using. This is called Friedmann equation. Okay? For completeness, let me write down another equation which I will use occasionally. This equation is 0,0 component of the Einstein's equations specified to homogeneous and isotropic universe with this particular choice of time. Another equation, which I will write down and erase very soon, is this one. This is ij component, the only coefficient of gamma ij, and it has this form: 2 dot over a plus a dot squared over a squared equals to pressure minus 8 pi gp, and also the special curvature term. Okay, this I will not use. In fact, the Einstein's equation, the system of Einstein's equations, is kind of there are more equations than variables. So some equations are redundant. This one is not going to be used. All right, that's one equation. We also need equations that govern the evolution of energy density and pressure in the universe. And these come out from covariant conservation of energy momentum tensor. So as promised, I'm going to erase this equation very soon. I erase it. Okay, so another set of equations, another equation comes from the covariant conservation of energy momentum tensor. d mu t mu nu equals 0. If you specify this, this is covariant derivative here, okay? If you specify this to this energy momentum tensor, then you get the only equation, the only non-trivial equation, which is covariant conservation of energy. When nu is equal to 0, it's a non-trivial equation. When nu is equal to spatial ij are 1, 2, 3. If it's equal to spatial coordinate, spatial index, then it's 0, because this is a vector, 3 vector. There are no 3 vectors in the homogeneous isotropic universe. So our second equation is the covariant conservation of energy momentum. You derive it, minus 3 a dot over a times rho plus p. So that's the system of equations you use, and also you need in the case of perfect fluid, you need a relationship between the energy density and pressure, and this is equation of state. So in perfect fluid cases, you just write that pressure is a function of energy density, and then you close the system of equations. Okay? Right, so we are at now coming to point 1.3 in this list. So from now on, I will be mostly using, without mentioning explicitly, the physically interesting case of spatially flat universe, kappa equal to 0. Although you can, generalize the results to non-vanishing kappa, but I will use kappa equal to 0 case as the most relevant one. So let me come to solutions to these equations. And they depend, of course, on the equation of state, right? So there are 3 interesting cases. One is radiation domination, meaning that the dominant part of the matter in the universe is relativistic particles, relativistic matter. Particles moving with speed of light. Okay? It's not today, it's not yesterday, but in the early universe that was the case. The matter was so hot that particles were relativistic there. In that case, pressure equals to 1/3 of energy density. Okay? And in fact, this is true irrespectively of whether you are in thermal equilibrium or not, what are the distribution functions of your particles. Once your gas of relativistic particles is homogeneous and isotropic, you always have this relationship between the energy density and pressure. Shall I illustrate this? Or it's clear? This is clear. Okay, it's clear. In that case, our second equation here is written as rho dot equals to minus 4 A dot over A rho. And therefore, energy density goes like 1 over A to the 4th power. And it's clear why. For free particles, it's obvious, because what's happening is that the number density of particles, relic photons, for example, goes like 1 over a cube, right? Like inverse volume. And frequency goes like 1 over A because of the redshift. Wavelength increases like A, frequency goes like 1 over A. So altogether, your energy density goes like 1 over A to the 4th. Okay? So this is radiation in general. Non-relativistic matter. Its pressure is 0 compared to energy density, which is mass density. And therefore, our second equation gives that energy density scales like 1 over a cube, just like the number of density. Since for non-relativistic matter, energy sits in the mass, then of course energy density scales like mass density, like the number density. And the third type of energy of interest for the time being is dark energy. And let me assume that dark energy is cosmological constant, lambda, or vacuum, which means that the energy momentum tensor is proportional to the metric tensor, rho lambda times g mu nu. Okay? Which is clearly covariantly conserved, since g mu nu is covariantly conserved. And you can interpret this as vacuum energy density, because for vacuum the only value, the only expression for the energy momentum tensor is metric tensor. In the locally Lorentz frame, it must be proportional to the Lorentz metric, Minkowski metric. Okay, this gives us that energy density is a constant, and this is consistent with the fact that pressure in this case is minus energy density, right? Because you compare ij components here, Tij, which is minus rho lambda delta ij for spatially flat universe, and you compare this with this expression here times a squared, of course, and figure out that pressure equals to minus energy density. So the rho lambda is constant, is consistent. This is consistent with the covariant energy conservation. So there are three types of energy in the universe, at least in the present and recent universe of interest. These are radiation, matter, and cosmological constant, or in general, dark energy, which may have in principle non-trivial equation of state, not necessarily P equals to minus rho, but the simplest case is P equals to minus rho. All right, so let me discuss solutions in these three cases. And so let's suppose that the dominant component in the matter of the universe is radiation. Okay, and let's neglect for the time being other components. So then my energy density goes like 1 over a to the fourth, and I get that a dot squared over a squared is equal to some constant divided by a to the fourth. This is our Friedmann equation with kappa equal to 0. And its solution is obviously a power law. A is proportional to power of time, and the power here is 1 over t. This one, t squared. This one should be also 1 over t squared. So A is proportional to t to 1/2. Okay? That's the famous behavior of the scale factor at the radiation domination. So t equals 0 is a singularity of the solution, which shows up both in the Hubble parameter, which is a dot over a, which is 1 over 2t, right? So the expansion rate diverges at t equals 0, and also from our Friedmann equation, we get that the energy density is, of course, going like 1 over a to the fourth. Well, it's just 3 over 8 pi g 1 over 2t squared. So it diverges. As promised, all the physical quantities are well defined here, whereas the scale factor itself, the coefficient here, is undetermined for especially flat universe. So we have a singularity, which is Big Bang singularity at t equals 0. The relationship between the Hubble parameter and time is proportionality. The universe has finite lifetime once the Hubble parameter is finite. And this brings us to an important notion, which is particle horizon. Suppose you emit a signal at the Big Bang singularity moment, at the initial time, t equals 0. You might ask, how far away is it from the emission point at a given moment of time, t? This distance is called, obviously, horizon, or more properly, particle horizon. So what is it? A convenient object, which I will use in the rest of my lectures most repeatedly, is conformal time. So let's recall our metric, ds squared equal d times squared minus a squared of t dx squared. Now I am in spatially flat universe. And let me introduce then conformal time, eta, which is dt over a of t. And the convenience of this conformal time is that the metric in this new time coordinate has conformally flat form. Here it is. Okay? dt is a times d eta, and therefore dt is a times d eta. You get this conformally flat form. And then that simplifies the analysis of causal structure, because in the conformal time and comoving coordinate x, the light, or signal speed going with the speed of light, travels just like in Minkowski space, right? ds equals 0, that's the null geodesic, is simply that d eta equals dx, right? It's a straight line, and the light cone is just like Minkowski light cone. Okay? So the coordinate size of the horizon is therefore eta, if I measure it from the Big Bang moment, okay? T dt prime, a of t prime. So this is coordinate size of the horizon. And the physical size of the horizon, LH, at time t, is simply, so this is coordinate size of the horizon, x. So physical size of the horizon is a of eta times eta. Okay? In these coordinates. Now, at radiation domination, our scale factor is this, square root of time, and therefore eta is equal to a constant, which is undetermined, since my scale factor itself is undetermined. It is not a physical quantity. So my eta is a, so let me write this way. A is c, where c is arbitrary constant for me. Therefore, if I write this fashion, then my eta will be 2 over c times t 1/2. And the physical size of the horizon will be twice, is that right? Yes, twice the time. 2 times t. Okay? Because a of eta is c times square root of time. Eta you integrate. It's twice the time. So the physical size of the horizon is proportional to the lifetime of the universe. It's a little bit bigger than the lifetime of the universe by a factor of 2, simply because not only the light travels, but also the universe expands, right? So that's why the physical size of the horizon is somewhat larger than the lifetime in light years. Okay. Here, this is a finite quantity which increases with time. Okay. So, or in other words, in the coordinates eta grows, and therefore the coordinate size of the horizon grows. Okay. So in our hot universe, or the same is true for matter-dominated epoch, the causal structure is as shown here. Okay, here is our Big Bang singularity. This is eta and therefore my light cones are the same as in Minkowski space. If the time passed from the Big Bang is short, then the size of the light cone is obviously small. So, for example, this could be a recombination. The time of the photon last scattering, or the last scattering of CMB photons. So this is a certain the horizon at recombination, the coordinate size of the horizon at recombination, and we are at eta 0 today, which is a lot bigger than eta of the recombination time, which means that we actually see a lot of causally disconnected regions, which were causally disconnected by recombination epoch. Okay, so what the cosmic microwave background tells us is how the universe is, what was the universe at this hypersurface, and interestingly, it contains, in the hot Big Bang theory, it contains a lot of causally disconnected regions. And immediately, this tells us that this is not true in nature. This is not the correct causal structure in nature. Right? Why? Because we have inhomogeneous universe, right? This is the famous picture of the cosmic microwave background. Remember, cosmic microwave background came from the time when the temperature was about 3000 Kelvin and the lifetime 380,000 years, very long ago. And the horizon size, we will calculate it very soon. The angular size of the horizon here, this diameter here, is seen at an angle of 2 degrees. We'll calculate that. Or I will show how to calculate that. So the horizon angular size is small, right? So if you want to, if this was the case, then all perturbations, all inhomogeneities in the universe should have the angular scale smaller than 2 degrees by causality, right? If you generate perturbations in the universe, inhomogeneities in the universe, in this theory, then their sizes must be smaller than the size of the light cone by causality, right? You cannot generate anything bigger than the light cone. So the question is, are there perturbations in homogeneities whose size is larger than 2 degrees? And the answer is yes. Here we are. These are blue spots and yellow spots, lower temperature, higher temperature on average, whose angular size is huge compared to 2 degrees, right? So this big blue spot could not be generated in the hot Big Bang theory. Okay, just looking at this picture, this is a photographic picture of the universe at the temperature of 3000 Kelvin. Thanks. Good, great. Looking at this photographic picture, you recognize that this pattern here, these large perturbations, large angular scale perturbations, could not be possibly generated during the hot cosmological epoch. So by naked eye, you understand that there was something before the hot cosmological epoch at which these perturbations were generated. That's why theory of cosmological perturbations is so interesting, because it tells us that there has to be something before the hot epoch, and the generation of cosmological perturbations occurred before the hot Big Bang epoch. Okay? Yes?
Can I write that equation for the perturbation or deterministic one?
Sure. Yeah, we will write down the equations. These are wave equations, essentially.
So it would be possible point of view, maybe not very practical one, that there was very, very homogeneous initial conditions, but not some previous epochs in the universe.
No, you have to you have to explain where all these inhomogeneities come from.
Because of initial conditions.
Oh, you mean the initial conditions that you had this huge perturbation at the very beginning. At this point and at this point, they're similar. Well, in principle, you can think in these terms, but it's very, unphysical, I should say. I mean, of course, you can build in everything in the universe from the very beginning and ask what was there. Well, okay, we'll come to that later. I take back. Well, in principle, since everything is deterministic, you can take the present status of the universe, go backwards in time, and figure out what the initial conditions are. Okay? Assuming, for example, that you are in the hot Big Bang theory, nothing else, then you're going to say that that they were very large in the distance, very long distance perturbations in the very early universe, which were built in as initial conditions. Yes, it's possible, but that's very unphysical. And it's worth trying to explain the origin of perturbations rather than imposing the very unphysical initial conditions in the for the cosmological evolution. Okay, let me come back to the Friedmann equation. Just for completeness, let me present two other solutions. One is not so interesting for the time being, which is meta-domination. It is important because there was a very long epoch of meta-domination in our universe. For meta-domination, you have that energy density goes like 1 over a cube. Again, with the you use the Friedmann equation here with kappa equals 0. On the left-hand side, you have 1 over t squared times squared, and here you have 1 over a cube. You immediately obtain that the solution is that a goes to like t two-thirds. Okay? That's in principle similar to radiation domination. Okay? In that you have finite horizon size. The horizon size in that case is 3 times t. You have a singularity, t equals 0, etc. So the structure, the causal structure, is similar. Finally, let's discuss lambda domination. And that's a different story. Suppose that the energy density, or energy density in general, is a constant. Then the solution is, then my Friedmann equation is that a dot over a squared equals to h lambda squared, where h lambda is a constant. H lambda is square root of 2 pi over 3g rho lambda. Okay? It's a constant. And since this is a constant, then a dot over a is a constant, then the solution is a is e to the h lambda times t. And that's an entirely different story. The metric with such a behavior of the scale factor is called the sitter metric. And the story with the sitter is completely different. If not for the other types of meta, if we had only this toy model, then we would have a completely different story, because the sitter metric, that ds squared equal to dt squared minus e to the 2h lambda t dx squared, doesn't have initial singularity. You can say, okay, if my time goes to minus infinity, then my scale factor goes to 0. However, you can always rescale the coordinates at given moment of time in the past in such a way that this metric is perfectly sensible. There is no small small parameters. Okay? So the system metric is non-singular. And in fact, you can read this in textbooks. In fact, this metric is a metric of a hyperboloid in fictitious Minkowski spacetime. So let me just tell you what it is, and then you can go to textbooks and read what the coordinate transformation is. So consider fictitious 5-dimensional Minkowski space with time coordinate y0 and spatial coordinates ya, a, 1, 4. Okay? And the Minkowski metric is, of course, ds5 squared is dy naught squared minus dy a dy a. Okay? Okay, this is 5-dimensional Minkowski space, and then consider hypersurface hyperboloid, which is y naught squared minus ya equal to minus h lambda squared. Okay, so this is a hyperboloid like this in Minkowski space. Here is y0, and here is ya. Okay, obviously this is a non-singular manifold. And then it turns out that by appropriate choice of coordinates, the induced metric on this hyperboloid can be cast in this form. Okay? I'm not going to write down, I can, but I will not write down the explicit form of this transformation, but you can, the explicit form of coordinates on the hyperboloid, but you can choose coordinates on the hyperboloid in such a way that the matrix on it has this form, induced from Minkowski metric. Okay? The interesting part of this is that this metric has a large symmetry. It's a symmetry of, it's a Lorentz symmetry in 5 dimensions, right? My hyperboloid is Lorentz invariant in 5 dimensions, so there is large symmetry group SO 4, 1. Okay? So the Sitter space is invariant under pretty large de Sitter group SO4, 1. So it's an interesting metric which doesn't have singularity. The particle horizon is infinite. What is particle horizon here? The particle horizon here, again, if we take the beginning of the universe to minus infinity, then the coordinate size of the horizon, particle horizon, would be like this, dt over t, right? And I take the lower limit of integration equal to minus infinity, since my beginning of time goes to minus infinity, essentially. Okay? And this is divergent, because A is this. As time goes to minus infinity, A goes to 0, and this is the divergent integral. So the horizon size, the coordinate size of the horizon, is infinite. But then you can think of another type of the horizon, which is called event horizon. This is a different concept. The particle horizon is the distance the signal can travel from the beginning of the universe. And event horizon is a different thing. Suppose I'm sitting at a point x equal to 0, and at time t, something happens at distance x from me, or physical distance x time a. Okay? Will I be able to know ever in future that this event has happened? Okay? Obviously, right now I can't tell, because I need the signal to come from that distance to myself. So it's not immediate that I will learn that something has happened. Will I ever be able to know what was going on there? Okay? That's a different story. In that case, what you're interested in is the coordinate distance from today, the signal, the distance to the signal that travels from today, t, to infinity. That's the maximum coordinate distance that signal can travel from today, t, to infinite time. Okay? So this is the coordinate size of the event horizon, which is integral from t to infinity e to the minus h lambda t prime dt prime, and this is 1 over h lambda. Okay? And I have chosen my scale factor equal to 1 today. So A is e to the minus h lambda times t. Plus. And here should write e to the minus h lambda times t. This is the eta, the coordinate distance, and the horizon size is 8 times eta, which is 1 over h lambda. Physical size of the event horizon is the inverse of the Hubble parameter. So I will never know what happens today at a distance bigger than h minus 1. That's why this is called event horizon. The universe expands so fast that I will not have any access to events that are happening today at such a large distance, larger than the inverse of the Hubble constant. Okay. So let me summarize the sample solutions. We had so far. By saying that at radiation domination, scale factor is square root of time, and eta is integral dt over A is also square root of time, and therefore A is proportional to eta. Okay? That will be useful in what follows. For meta-domination, we have A proportional to T to third. Eta is the same integral, well, it's proportional to T to 1/3, right? Integral dt over T to third is T 1/3, and therefore scale factor A proportional to eta squared. Finally, for lambda domination, A is with the e to the h lambda times t. Eta is 1 over h lambda minus 1 over h lambda e to the minus h lambda times t, and therefore the scale factor is minus 1 over h lambda times eta. Okay? In this case, eta starts from 0, and as the universe expands, eta goes to infinity. Here, eta belongs to minus infinity to 0. That's peculiarity of de Sitter universe. Okay. So that will be useful in what follows, that there are simple relationship between the scale factor and the conformal time, which is power law in all cases. However, in the case of lambda domination, it's inverse of eta, and eta ends up at 0. Okay, so to finish with this lecture, of course, we have all kinds of matter in the universe. So let me introduce standard notations again, which is, first of all, critical density. By definition, the critical density, it refers only these notations refer only to the present epoch. The critical density is such that that this equation is obeyed, meaning that if today the curvature term vanishes, then the total density, energy density in the universe is equal to critical density. That's the definition of critical density, and indeed, we know from observations that this term is small, it's less than 1%. And therefore, the total density in the energy density in the universe is equal to the critical density within 1%. Observationally and theoretically, it should be precisely equal to to the critical energy density. Numerically, this critical energy density is 5 times 10 to the minus 6 GeV per cubic centimeter. You just plug in numbers, you do the translation from centimeters to GeV or whatever, megaparsecs, etc., you get this number. Okay, now then one introduce omegas. Oops. Then one introduces omegas, which is the ratio of a given type of energy density to the critical energy density. Okay? And also one introduces the omega curvature, if there is curvature, which is the relative contribution of this curvature term to the Friedmann equation, okay? Which is minus kappa over A naught squared H naught squared. Okay? And observationally, this omega kappa is less than 1%. Actually, it's even less than that, 0.007. That's the Planck bound combined with others, with baryon acoustic oscillations, etc. So this is small. Why is all this notations useful? That's because by using this omega, you can cast the Friedmann equation in a suggestive form, which is h squared equal to h naught squared, right? Now, omega radiation times a naught over a to the fourth, right? By the way, sum of these omegas, including curvature, is equal to 1 by definition, right? So there is the non-relativistic matter, a naught over a cube. Then dark energy, if it's constant in time, then it's just a number, omega lambda, plus omega curvature, a naught over a squared. Right? That's an equivalent form of the Friedmann equation in the case when you have radiation, matter, cosmological constant, and curvature. Right? Because, well, that's clearly the case, right? Which tells you that now the content today is that amazingly omega matter is about 25%, sorry, 30%, which dark matter gives about 25%, and baryons about 5%. Okay. The more precise values you can get from particle data group publications. So I'm not going to give precise numbers here. They vary from experiment to experiment, but that's more or less the outcome. Now, omega lambda is 70% accordingly. Now, there is some tricky thing about the radiation. But let me postpone it for a short time. We certainly have relic photons that contribute to radiation, and possibly massless type of neutrinos contributing to radiation. Well, certainly this omega r is not equal to 0. So this form of the Friedmann equation tells you that while today the dark energy starts to dominate, this wasn't the case before, because earlier on, at smaller a, this term was dominating, right, over the cosmological constant. And even earlier, the term which is most singular as a goes to 0 was dominating, right? This is radiation domination. So the sequence of events is this. You start off with some unknown, yet unknown epoch, where, as I alluded to, the cosmological perturbations were generated. Then we had radiation domination, then matter domination, and now we are in transition epoch to lambda domination. Okay. Curvature term was never important, because today it's smaller than the matter contribution, a lot smaller, and earlier on it was even smaller, since its behavior is 1 over a squared. So the curvature was never important in the evolution of the universe, but radiation was at the early stage, matter was at later stage, and now we are in the transition to the lambda domination. Okay, now one important moment of time, there were epoch. There were several important epochs in the cosmological evolution. One is the recombination epoch, or photon last scattering epoch, and I'm not going to go into physics of that epoch. It's an epoch at which the plasma phase of the baryon photon component and electrons became a gaseous, when the transition from plasma to gas occurred, and that happened, as I told you, when the universe was 380,000 years old, and the temperature was about 3,000 Kelvin. That's the recombination. That's a physically interesting time. Another interesting time is equality between radiation and matter. The time when equality. The time when the energy density in radiation in the relativistic matter was equal to matter energy density. Okay? It was pretty early epoch. We know what is the matter energy density. We just have to scale it with the scale factor. Now, about radiation. For understanding when this epoch happened, one treats neutrinos as massless, because at that epoch the temperature was higher than the neutrino mass. So one treats neutrinos as massless, and for massless neutrinos, so massless neutrinos, one can think of them as a relative particles, as a gas of particle with a certain temperature, and the neutrino temperature is actually smaller than the temperature of photons by a famous factor 4 over 11 to the power 1/3. I'm Not going to go into the calculation of this factor, but it has to do with the following. Neutrinos decouple at temperatures of about 2 to 3 MeV. Before that, they were in thermal equilibrium with the baryon photon component and electrons, and they decoupled at temperatures of 2 to 3 MeV. At that time, in the plasma, there were photons and also E plus and minus pairs, right? But as the universe cooled down, the neutrino temperature decreased simply because of the redshift, whereas the photon temperature did not quite decrease like that, because there was annihilation of E plus and minus pairs into photons at lower temperatures, and this annihilation heated the photon gas. So it added energy into photon, it added entropy into photon gas, and therefore the photon temperature is higher after E plus and minus annihilation epoch. The photon temperature is higher than the temperature of neutrinos. And vice versa, the temperature of neutrinos is lower than the photon temperature. Okay? So this is due to the heating of the photon component during E plus and minus annihilation, which occurred after neutrino decoupling. Okay? Now with this, you can then calculate, pretending that neutrinos are massless, you can calculate the radiation energy density today by Stefan-Boltzmann law. Okay? For photons, it's 2 times pi square over 30 photon temperature to the 4th power. This is just Stefan-Boltzmann law. For photons, 2 is number of polarizations. For neutrinos, you have number of neutrino species, which is 3 in real case. Number of neutrino species times 2 polarizations of neutrinos and antineutrinos. There is a Fermi factor 7 over 8, and the same pi squared over 30 times 10 to the 4. That's the present temperature. Okay. Now the present temperature of photons, 2.726 Kelvin. So we know the energy density in photons, and we calculate the energy density in neutrinos. Okay? And that's not negligible. That's more than half of the photon energy density. So this is neutrino to the 4th power. Neutrino temperature to the 4th power. Even though neutrino temperature is lower, still it's not much lower, and therefore neutrinos contribute quite substantially to the energy density of radiation. And from that you immediately calculate omega radiation, which is 2.6 times 10 to the minus 5. And this gives us the redshift at equality, because what you need to have is that rho present value of the omega radiation equals to 1 times 1 plus z equality equals to omega meta, right? Scales like 1 over 8 to the 4th power. This scales like 1 over 8 cube. So this is remaining 1 over a. Okay? And from that you calculate the redshift. The redshift is at about 3.5 times 10 to the 3, and temperature is about 0.8 eV. Whereas for recombination, temperature is 0.26 eV. So equality between radiation and matter occurred before before recombination, before photon loss scattering. So here is a summary of today's lecture. We are here today. Lifetime of our universe is 13.8 billion years. In the future, the cosmological evolution will be governed by dark energy, will be dominated by dark energy. Today, it's a transition time, and from that, about 0.6, the universe accelerated its expansion. I forgot to say, but it's obvious. I should have said in my summary that at radiation domination, A goes like T to 1/2, and therefore A double dot is negative. Same with matter domination. A is T to 2/3, A double dot is negative. This is decelerated expansion. And at lambda domination, A is e to the h lambda times t. Therefore, A double dot is positive. So when you transit from matter domination to lambda domination, you also transit from decelerated expansion to accelerated expansion. And you can calculate the redshift at which the universe started to accelerate, meaning that A double dot changed its sign, and that is about 0.6. So we have an epoch of last scattering of CMB photons. As I told you, it's about 380,000 years, temperature is 3,000 Kelvin, redshift 1090. Early on, there was a radiation matter equality, which happened when the universe was about 70,000 years old, earlier, and the temperature was like 3 times larger than at recombination or last scattering. Now there is another epoch which we have direct experimental data from. It's nucleosynthesis epoch of formation of light nuclei in the universe via thermonuclear reactions. It's one of the cornerstones which I had no time to talk about. It occurred from 1 second after the Big Bang to a few minutes after the Big Bang. There were probably epochs of generating dark matter and asymmetry between matter and antimatter. That's not the topic of my lectures here, but it's interesting epochs which we can hypothesize only for the time being. And what we are going to discuss towards the end of these lectures is this epoch, which is marked by question marks. So that's the summary of hot cosmological stage in the nutshell, and we'll discuss how the perturbations behave during that epoch, and that will tell us a number of things about their generation. Right, I think I'm done. Questions?
So questions?
Could you explain why the equation of state for radiation is P equal to 1/3 of rho, even if not in thermal equilibrium?
Okay, let me give you a very simple argument. Based on scalar field theory. Okay, so let's consider massless scalar particles. Okay, and you can do the same thing with the photons or fermions, doesn't matter. But for scalars, it's very obvious. The action for scalar particles is this. For scalar, it's square root of g minus g, half of g mu nu d mu phi d nu phi. That's all. Okay, so energy momentum tensor. By definition, it's twice delta S over delta G mu nu. Okay, and it is equal to here, 1 over square root of minus G. 2 over square root of minus G. And it is equal to d mu phi minus G mu nu and 1/2 of G lambda rho d lambda phi d rho phi. Okay? This could be a massless scalar field, it could be an operator, doesn't matter. Okay? So, this is d mu phi. Okay. Now, these are massless fields. So d mu for a given mode is k mu, right? Where k is the momentum. So t mu nu is the sum over modes with given momenta, and each mode contributes like this: k mu, k nu, phi squared, minus g mu nu, 1/2 k mu, k lambda phi squared. Okay, that's the contribution of to the energy momentum tensor coming from a mode of a given momentum. Okay. Now this is k squared. This is 0. Right. I'm in the locally Lorentz frame where metric is Minkowski metric. So this is 0. So T naught naught is k naught squared, phi squared. Tij is ki kj, phi squared. Then you have to sum over all modes, right, with distribution functions. Now, if my field is homogeneous and isotropic, so I use homogeneity by, writing this in the Fourier space. And if it is isotropic, then ki kj averaged over in angles is just 1/3 of k squared, right? Delta ij, of course. So angular average of ki kj give you 1/3 of k squared. And so this Tij averaged over angles is 1/3 of k squared phi squared. And of course k naught is equal to k modulus of k for massless particles. So this is pressure, delta J. This is pressure, this is energy density, you get 1/3. So the only thing you need is homogeneity and isotropy of your gas of particles or massless fields, then immediately you have this property.
Other questions?
All right, I'm around. If you have questions, you can ask them privately.